Hello and welcome to RATA Skillathon 2026. This is the second season of the Skillathon. Last year we had similar programs, and this year again in the month of July, we're going to spend our time on learning new things. Today we have a very interesting speaker from Danfoss. He's going to talk to us about the heat pumps and the recovery systems by recovery systems. So I'm happy to introduce you to Mr. Ninand Prabhudesai. He's the Deputy Manager Applications. Thank you, Ninand, for taking time out to sharing this information with us. And we look forward to your session on heat pumps and recovery systems. Thank you very much.
Sure. Okay. Thank you, Ajit. Hello, everyone. So I'm Ninand Prabhudesai. I work in Danfoss in client application team. So today I will touch upon the heat pump and heat recovery system. I think heat pump is kind of a very big topic nowadays in India as well, considering its more and more demand. So we will see what are the heat pump types, how heat pump works. We will start with basics, and also we will try to cover upon the recent trends in the heat pump market and what are the refrigerants and the technologies are going on and getting developed. So I'll just start with the basic thing, that is what is heat pump. So basically heat pump is nothing but which takes the low temperature heat from the ambient, whether it's ambient air or ambient water, or from the ground for that matter, where the solar energy is getting trapped. Then it pumps the heat to the higher temperatures, and then it gives to the respective spaces where the requirement of heating is there. So this is a simple function of the heat pump. The working principle is basically whenever the heat from the ambient is absorbed, it is given, or it is compressed by the compressor and elevated to a higher temperature. So for that, of course, compressor consumes the electricity. That is what we call as compressor power in kilowatt. And then the total heat rejection of the heat pump is nothing but your ambient heat absorbed, and then plus the electricity what compressor is using. So the total heat output of the heat pump is the addition of the both. So if you see the schematic of the heat pump, of course it is very well known to us, because it is similar to chillers, what I would say. Of course there are few differences since the functions are opposite to each other, but the basic components like compressor or the evaporator, condenser or the expansion valve, or the other line controls in the system are basically the same. Only thing is that they work probably in a different way. So how, that we will see later. But currently in this schematic, you can see on the left hand side from the evaporator, the low temperature ambient heat is being absorbed, and then it is being elevated by the compressor. You can see the red color over here, which is basically the high temperature heat, and that is being rejected where your heating requirement is there. And then it could be the water, or it could be the space where air has to be heated up. So that is basically your heat rejection where it happens. So now you must be familiar with the term called COP. So it is similar to chiller, but in heat pump we calculate this COP based on the heat power output and not at the cooling capacity. So because here we are measuring the heat rejection of the heat pump. So here COP is nothing but your heat pump's heat rejection output divided by whatever the power is being consumed by the compressor. So here in this example, let's say if total heat rejection is 38 and your compressor consumes the power of 10 kilowatt, then it's nothing but 3.8 is your COP. But what happens is COP is always calculated at a particular condition and at a particular moment. So over the period of 1 year, if you see, there are a lot of changes on the ambient, there are a lot of changes on the demand. So your COP cannot be, the actual efficiency of the heat pump. And that's why we do have the next parameter, which is nothing but the seasonal performance factor or seasonal efficiency of the heat pump. So here we consider generally the annual period the period of 1 year, and we understand or take average of all the COPs throughout the year. So basically, here what happens is the total heat rejection throughout the year, what heat pump has given, divided by the total electricity what compressor has consumed. So overall we get kind of the average COP, considering all the other variations that affects the heat pump working. So here in this case, let's say the heat pump consumes around 6,000 kilowatt of electricity, and let's say 19,200 is the total heat rejection. Then your seasonal COP is basically 3.2. So that gives you the idea of actual efficiency of the heat pump. So moving ahead, we will look at the what are the types of the heat pumps. So in chillers, probably you must have heard about air cooled condensers, or what that means, water cooled chiller or something. But in this case, there are multiple combinations. So those combinations are based on the whatever the heat exchangers we are using in the heat pump on both the sides, like on the evaporator side or the condenser side. So in this, there are typical types of heat pumps like air to water, or air to air, or water to water. So these are very simple nomenclatures. So if on the evaporator side you are absorbing the heat from the ambient air, then you use the air cooled heat exchangers like microchannel or Finan tube. And this, on the other side, if you are delivering the heat rejection to the liquid like any brine or water, then there you use generally the PHE or shell and tube heat exchangers. So then that becomes your air to water or air to brine. If on the ambient side you are rejecting the heat from the air, and also on the heating side you are using that air to heat the air in the room or in any specific building area, or in any specific dedicated area, then that becomes your air to air. Similarly, for water to water is basically on the evaporator side also you have PHE, where you are supplying cold water, probably from cooling tower or so. Then we are absorbing heat from that particular water, and then delivering that heat on the other side. So if it is air cooled on the other side, the air heat exchanger, then it is water to air, or then again, if it is a brine on the condenser side, then it is water to water or brine to brine. So based on these working of the heat exchangers, these heat pumps are basically termed as air to air or air to water, like that. So the other type is basically the reversible heat pumps. We also call it as a chiller slash heat pumps, because on the cooling side it gives you the working of the chiller, and the heating side it gives you the working of the heat pump. So in this case, what happens is, let's say during the period of 1 year, if the ambient is fluctuating from, let's say, 30 degrees to 0 degrees, or -5 degrees, then in that case you need both. Like in the summers you need the cooling, and in the winters you need the heating. So in that case, the same heat pump can be used as a in a reverse way. So in this case, you can see there is a four-way reversing valve, and if there is a heating cycle, or the normal cooling cycle, let's say, so in that case, compressor discharge is going to the condenser, and then through the expansion wall it is coming to the evaporator. Now let's say you want the opposite cycle, then this four-way reversing wall will move the cooling cycle, and your discharge will go from this side, and then your cycle will be reversed, and where you were getting the heating, there now you will get the cooling. So this is a very common example of reversible heat pump, where you can use either one expansion wall, or single expansion biflow wall, or two expansion walls. So that reversible heat pump is one of the other types. Then the next thing is about balancing the heat demand and the heat capacity. So generally what happens is, during the larger temperature range, when the heat pump is expected to work, we always consider the worst case. So in that case, your worst case of the heating is basically at the lower ambient temperatures, where your heat pump capacity drops and you need more, you have a more demand in the heating side. So you can see on this graph, whenever your ambient increases, your heating demand reduces, but your heating capacity of the heat pump increases, because basically here your ambient controls the evaporating side of the heat pump. So ambient increases, evaporating increases, your heat pump capacity increases, and it's vice versa. So to meet this lower ambient capacity, we are unnecessarily designing this heat pump in a bigger size to meet this. But at the rest of the time, it is not actually required. So what generally the process followed is that for the particular section, the other source of energy, like let's say electrical heater or the gas boilers, are being used for only for that particular number of hours, let's say around 700 hours in a year, where your ambient is going below 5 -5 degree. So there you can use that and reduce the size or optimize the size of the heat pump. So balancing the heat demand with the heating capacity is very important in terms of avoiding your heat pump getting unnecessary bigger, saving high cost of it, saving high working cost of it. So then that has to be balanced. So for that matter, the hybrid heat pumps, where, as I said, the secondary source of heating is used for a particular period of time. So that gives you a smaller, gives you the benefit to go with the smaller heat pump. First, it saves the cost and the electrical load. Then you can have a flexibility. Like if you really have a bigger demand, then you can actually use that electrical heater whenever you need, and or the secondary source whenever you need, and you can meet the requirement. So and also sometimes if your requirement of the heating is faster, like let's say you need instead of 10 minutes you need in 5 minutes, then also you can use this secondary heat source as a boost for it. So there are multiple benefits, and that can be utilized when we go for a hybrid heat pumps. Yeah. So next is basically the temperature requirements. In India, we have a large market for the industrial heat pumps, because in residential, generally we use in the other hospitals, or basically the smaller requirements where you don't need much of a temperature of the water or the heating space, and also in the swimming pool applications and all. So in India, basically in industrial applications where the processes are there for, let's say, for automobile or for pharma or for brewing industry. So there you need the higher temperature water outlets. So you can see in this generally we have the heat pump market currently matured for up to 100 degrees of water outlet temperature. But if you go above that, of course, there are developments going on, and many products are being launched into the market so far. But the population of those heat pumps is quite less. So 80 to 100 degree is now very comfortable range in the market, and there are many different refrigerants we will look forward in the upcoming slides. So from this slide, what I would like to give a message is that there is a tremendous consumption of the process heat in the different processes, and 100 to 150 degree is now a bigger segment, where probably around the maximum wattage is being used, and the developments are going on. So, and how also it will help in saving the carbon footprints, or the the electricity savings that we will see from one of the examples of brewery process diagram. So in this you can see there are multiple heating and cooling alternate processes, and the heating you require maximum, let's say 95 degrees, whereas cooling is required at 4 degrees or 15 degrees. So here earlier days, people are using the fossil fuels for using or burning they were burning the fossil fuels for using the heat or heating the whatever the process requirement is. But now we can combine it with the cooling and heating both the modes, or in a one particular side we can use evaporator to cool the product or cool the water to 4 degree, and at the same time we can use it to heat it to, let's say, 70, 80 degrees or 90 degrees. So that is now getting combined. So instead of having two separate systems, that too one with the fossil fuels and wasting the energy in that. Instead of that, we are now clubbing it. So you might have seen many examples where we are heating the water to 90 degrees, whereas on the cooling side we are taking the byproduct of the cold water, and that is again being used for the different processes. So that is the key advantage where we can save a lot of energy, and lot of decarbonization opportunities are there. The simple example which I have tried to just put up here is why do we use heat pump? Why do we use heat pump? Is basically, if you see the different kind of heating fuels like wood or coal or natural gas. So I've just tried to summarize over here that if you are yearly, if you are using, let's say, 12,600 of kilojoules per kg, then you need around 8 INR of the cost for the running of the HP, I mean the heat pump. So whereas for the wood boiler, it will be like 5.5 kgs. Of course, wood is quite efficient, but then again, wood is like again, where from where we are getting. So we have to cut the trees and all those environmental impacts are there. Whereas if you see coal and natural gas, of course, heat pump is much efficient because of the prices, first of all, of the fuel, and also if you see the efficiencies, so around 80% or 70% the efficiency. So then there heat pumps are the clear winner, and that is. And if you compare with electrical heater, then there is no doubt, because electrical heater generally consumes 1 kilowatt per unit, but whereas we have a COP of around 3.5, where we use 3.5 kilowatt just from the 1 kilowatt of heat. So there is no comparison at all with the heat pump. So just to back up my last comparison, I have put up here one heat pump case story, where from Danfoss, actually we had a collaboration with our partner, and we gave this heat pump to the end user in Pondicherry, and this was used basically for the automobile process, 7 tank process, where they had a requirement of 90 degrees of water outlet temperature. Initially, they were using the diesel generators, and the diesel consumed was close to 50,000 liters per year. So you can imagine the cost and the CO2 emissions for that. But when we gave this heat pump and when they installed it, the 90 degrees water outlet was produced with this heat pump, where we used R1234ZE, which is first of all a low GWP gas. It has the GWP less than 7. So GWP is basically global warming potential, and the whole world is now moving towards more and more development of the low GWP gases. So we use this R1234ZE. They are this is a realized saving of 2.3 million INR, which we have cross-checked with the customer, and the customer is really happy for that. The payback period, that's why, reduces significantly. And also the main part is about the environmental effect, which I already explained. So we have saved almost 87,000 kgs per year of the CO2 emission, because they were using 50,000 liters diesel into their generators to heat this. So this is what the impact a heat pump can produce, and the benefit it can give. So when we say that the heat pump is efficient, it also has a fuel which we call as refrigerant. So in that case, more and more refrigerants are coming into picture, just because of the drive that is happening to reduce the global warming potential and to go towards natural refrigerants, or the GWPs which are lesser than 150. So I would say in India we have already banned R22. We are in process of banning this 407C or 134A, and moving towards the low GWP gases like R1234ZE or 454B, 452B, 454C, or the natural refrigerants like CO2. In that case, if you consider the heat pump market, so on the screen you can see this is a flammability line of the refrigerant. So below this, all are kind of either A1, A2, or A3, mildly flammable or the highly flammable refrigerants. But they have the low GWP. So on the left hand side, you can see the GWP values are mentioned. Whereas on the x-axis, it is kind of the volumetric efficiency. So let's say if R134, if I consider, and 410, then of course 410 has a very big capacity. It gives better heat efficiency. So in that case, now since 410 is commonly used in the process heat pumps where you need the water up to 60 degrees or 65 degrees, but now that is also getting slowly phased out, and people are moving toward the drop-in replacement like R452B or 454B. Whereas for the R134A, now the market is moving towards R1234ZE or R600A, R1234YF. And for the very high temperature heat pumps like above 140 or 145 degrees, I think they are going for the R1336 MMZ and also the R245FA. Of course, these gases are having their own challenges in the system. They are not certainly not the always the dropping replacement that we I just simply remove the 134A and put R600A or 1234ZD. It's not always like that, and that is why there are a lot of new developments going on in the products. Let's say a compressor or the electronic expansion valves, where they are qualifying these components for the higher temperature ranges. So now most of the demand what I can see for the higher temperature is with R600A or 1234ZE. That we will see in the upcoming slides where compressor how the compressor can benefit with these gases. So for heat pump market, I think these are the two refrigerants. Whereas CO2 is also slowly popping up because it is a bit complicated system. But of course, now there are experts in industries who can help. Rather in Danfoss also we have the one particular dedicated team for driving these projects. So we'll quickly see the other heat pump components, of course, compressors and all that we have already seen in the schematic, but also there are many other components which goes into heat pump, and the benefit or the there are different features of it which can benefit heat pump working. So certainly the first one is the compressor. So in compressor technology, there are of course screw, scroll, and the semi-aromatic reciprocating compressors which are being used already. Now, as I said, there is a requirement of up to 150 degrees of heating into the process. So in that case, of course the existing components cannot be used as it is because they were not qualified for that. But now slowly the organizations like Danfoss are coming up with this new series of compressors and all other line controls. So in this case you can see first of all the common technology which is being used is liquid injection valve, because when your compressor runs at the higher pressure ratio, let's say your ambient is close to 0 degree and you need the water outlet of around 70-80 degrees, then you have a very big pressure ratio. So your compressor gets heat up, and to cool it down and to reduce or keep your discharge temperatures within the limit, there is a liquid injection technology available. Then you have the economizer system also. This is a very common system, but what compressors are now coming are with the mixed technology. Basically, they will have the economizer circuit also and liquid injection also. Liquid injection will only turn on based on your discharge temperature. So if your discharge temperature goes above certain limit, then your liquid injection will start for a moment, and then again it will switch back to your economizer circuit. So it is called as kind of a wet injection where the compressor temperatures are kept within the limit. Economizer is obviously giving benefit into your efficiency and the capacity of the heat pump or the compressor. Then, as I said, envelopes are envelopes of the compressors. These are working envelopes of the compressor, which are getting extended day by day, considering the requirement of the temperatures from the market. There are gases like R600A or 1234ZE, which are being qualified into the scroll compressors. where you can achieve around 100 degrees of water temperature or 90 degrees of water temperature very comfortably. Whereas in semi-hermetic compressors, you can see the envelope on the right hand side. It is already being qualified up to 120 to 123 degrees of condensing, so that you can get the pressurized steam or water temperature up to 120. Whereas with R1234ZE, again, it's close to 90. And then R290 is also coming into picture. Of course, it has some limitation due to its flammability, but the charge limitations. But still, it gives very good thermal efficiency, and that is why with a very small charge also you can get good capacities, and you can make systems up to bigger systems nowadays. So these are the few important refrigerants in the market currently, and these are the developments which are, I would say, already released into the market, and the demands have started coming for using these compressors up to 120 degrees also. Yeah, the next part is heat exchanger. Of course, we have the BPHE, which is on the right hand side. You can see with the fishbone arrangements, but the more and more efficiency we are expecting from all the components, and that's why these developments are always going on. Where you can see on the left hand side there is a microplate heat exchanger. So microplate heat exchanger is basically it's a brace type plate exchanger only, but it will have the plate design as a dimple design. You can see small dimples over here. This is basically to increase the heat transfer area in the same size of the PHE, and to give better and better heat rejection or the heating capacity. So with the same size, you can probably get more heating capacity in that sense. Then, as I said, explained about the reversible heat pump. So four-way reversing wall are being consumed or used in this. Basically, they are the key drivers for changing the reverse or changing the cycles from heating to cooling or cooling to heating. Then, of course, the line control. So, electronic expansion wall has a now wide range. It can work up to probably 110 or 120 degrees also with this new refrigerants, like 1233 MZZ or the 1234ZE. And in that case, you need the you need the controller, superheat controller, or the wall driver for that. You need the transmitters which can work up to that particular temperatures and pressures. Then you need the temperature sensors up to that range of temperature. So all these products are now being qualified and are into the market. Then, of course, the reversible heat pump, you need the biflow filter dryer, which can filter out the things or the pollutants or whatever the moisture is there in the system, and it should not release it when your system turns from heating to cooling or cooling to heating, because it should retain that moisture or the particles into it in both the flows. So that's why there's some special arrangement inside it. It is done, and then these products are being used in the reversible heat pump. Then there are few heating cables which you can use in the lower ambient temperatures to avoid any kind of freezing on the evaporator side, because condensation happens due to lower temperatures on the evaporator side, and then probably the droplets can go into the pan and get frozen over there. So that's why there are electrical heating cables are available, so which can be used on the lower ambient applications. Okay, so I think that was all about on the heat pumps side. The other topic which I just wanted to touch upon is the heat recovery system. So there is a minor difference between the heat pump and heat recovery system. Heat recovery system is basically we are not going for a very big condensers over there, because here we are just using the sensible heat from the refrigerant to heat the water. So heat pump and I mean heat recovery unit can be used in existing air conditioning system, and this is a very good tool to save the cost. That also one of the case studies I will explain in the upcoming slide. So how does it work basically? So after the compressor, this unit is placed, and here you have a heat exchanger where from one side the hot superheated discharge gas from the compressor is being circulated, whereas on the other side you have a water tank and the secondary water circuit where the pump will keep on circulating the water throughout it, and then it will get heated up because of the heat of the or the heated gas. There are two major advantages. One is this energy is, or the heat of the gas is anyway being rejected in the condenser, so your condenser is getting loaded because of high temperature inlet gas. And second thing is, this energy is free actually. It's, we are simply going to reject it into the ambient, so that we are consuming here in the heat recovery unit, and to use that energy to heat some water or brine, whatever as per the requirement. So in that case, you get both the benefits, that your condensing temperature probably could be, benefited by 1 degree or so, where your heat pump or the chiller capacity can be increased. Secondly, on the other side, you get the water, heated water or heated brine, which we are using currently, let's say with the electrical heater, or heating it with some other natural sources. So both the advantages are there, and it's a very simple unit. We are just diverting the gas to a PHE and using it to have a heat transfer and heat the water on in the tank. So there is a actually case study on this where Danfoss has already installed this in their campus in Chennai. And earlier in the canteen, whenever the water requirement was there up to 60 degrees for cleaning the utensils and all, that was being done through the electrical heater. So the consumption of the electrical or the power consumption was almost 200 250 units per day. But there was a system of 24 TR air conditioning system which was already was in place to for the cooling of the canteen area. So in that only we have incorporated this heat recovery unit. We have not done anything else apart from that. We have just installed the in the existing system. We have not changed the compressor. We have not changed any other components in the system. And with this now we are producing 1500 liters of water every day of 60 degrees in canteen, which has saved almost 250 units of electricity per day. So that you can just imagine how much saving is there for a year. And of course the that's why the ROI is also quite less. So this is very important, and very easy way to do the decarbonization, or to reduce the electricity consumptions. With this, I would say we have also the ready-made catalogs for it, where you can simply go and select if you have a 2 TR system, if you have a 5 TR system, or 10 TR system, then what are the components are to be used, sizing of it, the models of it, everything is ready. So that heat recovery unit catalog is available. And I would suggest all the big organizations over here who have the canteen facilities, or who needs the higher temperature water daily for their different uses in the premises, they can simply put this heat recovery units and get benefited out of it. Yeah, so I think that was my last slide. Ajit, I would hand over to you now.
Great, Ninand. Thank you so much. That was really informative session, especially with those case studies. It kind of validates the theory and actual application.
Exactly.
So that's absolutely fantastic. And I'm sure all the engineers or even the business owners who've actually gone through this program today has really benefited from this. The big advantage, Ninad, that we have is, this is on YouTube. So we're not forcing anybody to sit and see the entire program only once. And if you're busy, stop, see it again. If you want to see it again and again, see it and again and again. So that's the whole idea. The idea is to actually push as much as knowledge out there so that the overall quality of the industry increase. And people like Ninad stepping out and taking time out to share this information goes a long way, because this information is available forever. And we can also keep training more and more people around. So Ninad, thank you so much for taking time out. And it was a fabulous presentation. Thank you very much.
Thank you, Ajit. Thanks. It's my pleasure. Thank you.
Thank you. Thank you.
From the land that celebrates innovation and breeds enterprise, comes the next chapter of India's HVAC and HR journey. 3 cities, 4 milestones, 1 vision. RATA Conclave, India's most powerful platform for HVAC and R entrepreneurs, thinkers and changemakers. And now in 2026, we converge in Ahmedabad, the growth capital of the West, where business meets purpose and sustainability meets scale, empowering HVAC and R business for sustainable growth. 1,000 plus delegates, 70 plus industry speakers, 80 plus partners, 3 power-packed forums, national MSME awards, live networking and product showcases, a marketplace of ideas where innovation scales, connections deepen, and opportunities compound. Experience it all in the soul of Gujarat, culture, cuisine, and celebration. Only in Ahmedabad. Join the movement for MSAMS to thrive, manufacturers to evolve, and the ecosystem to advance. Mark your calendars 25 and 26 September 2026.